Let me show you how I made this globe with panning and zooming. You can click and drag and zoom in and out, and it always stays such that the North Pole is at the top. This is an adaptation of the previous spinning globe example, for which there is a whole video by itself. In this example, when we unpack the state, we have the rotation, scale, translation, and initial scale. Rotation and scale are the things that change when you pan and zoom. Here's the code that initializes the rotation, same as it was before. Here's the code that initializes the scale. Now this is something new actually in this example. I'm using fit extent to get it to fit to the screen. This makes it so that when you load it in a full screen view, it fits properly on the screen. So notice if I resize the window and refresh, it is fit nicely in the center there. And also if I have a vertical screen and refresh, it fits to the center there as well. And that's because we are using fit extent based on the margin and the width and the height. And I wonder if we need that 2 times the margin. I was looking at it, it seems a little bit off. Okay, now it actually seems more correct. Now if I refresh, okay, the space on the bottom and the top is the same. Okay, looks great. I didn't go all out and make this thing responsive, but at least I made it show up nicely when you load the page. So it would work well for embedding, for example, if you wanted to embed this on a page. And by the way, if you make something that you want to embed in VizHub, you can get that out of the box by just clicking Share, Embed, and copying this link. And you can even do white label embedding, where no VizHub branding will show at all. And you just copy this and paste it into your CMS or your HTML. But anyway, so yeah, fit extent is a method from D3Geo. I think most or all of the projections have this method. And you specify a 2-dimensional extent using this array of nested arrays where this is x, y, and I'm using a margin here that's the same on all 4 sides. And then this is the xy of another point. And these 2 points specify the bounds or the extent that you want to fit to. And passing in type sphere is sort of a secret incantation that magically works. This is the definition of the whole Earth, which you can see as this sort of outline around it over here. So that's how we get the fitted projection. And then based on that, we call .scale, and that it becomes our initial scale. And we also have fitted projection.translate. And this is important for moving it into the right position. And keep in mind, all this happens once, just on page load, essentially, when scale is undefined. So after we figure all that out, we call set state using immutable update patterns to set the initial scale, the scale to be the initial scale, and the translation to be the initial translation. And this might seem weird right now, but it turned out that to get the panning and zooming working, I had to have a reference to the initial scale. So initial scale, I just put it on the state, and then scale is initialized here to initial scale, but over time, scale actually changes when you pan and zoom, whereas initial scale on the state does not. So that's how we initialize the scale, and the initial scale, and the initial translation. We render the map just like we were before, and I set this up so that the drag behavior and the zoom behavior are defined outside of the map itself. So if we look at the map.js, it's still very simple, but it does a couple things that it wasn't doing before. Namely, it sets the rotate, scale, and translate on its projection instance based on the values that we pass in every time we render. And then it's just the pretty straightforward rendering logic for the sphere, the graticules, and all the countries. So that's map.js. No interaction logic at all. The interaction logic is here. So there's a part that sets up a drag behavior, and there's a part that sets up the zoom behavior. These chunks of code instantiate a drag behavior similar to the drag behavior that we had in this other example with the circles, and also a zoom behavior similar to this other example that we had with the circles. Those two videos might be good to review if you feel lost on this. So now we're pulling together those concepts to implement this panning and zooming on the globe. All right, here is the code that sets up the drag behavior. This is the panning part of the panning and zooming. I think this is so cool because we can leverage D3's drag setup that it has. And look at this code. It's so small and it gives us so much. But how? Well, we're using svg.call to call this drag behavior instance, which we are instantiating on each render. And then we're adding this event listener for drag. So every time you move the mouse, this function here gets invoked with the event and the dragged datum, which actually was left over from before. I don't think we need that one. Yeah, now it still works. Now here we are using the setState function with immutable update patterns, passing in a new version of the state with all the old properties, but the only thing that changes is state.rotation. And rotation is this array of 3 elements, x, y, and I guess z, or pitch, roll, and yaw. I can't quite remember. But it defines how the globe is rotated. So we're only changing the first 2. The first one we're changing based on x, so that's this way. And then the second one we're changing based on y, which is this way, up and down. To get the new version of the first element of this rotation array, we start with the old version from the previous version of the state of the same entry, and then we add to it event.dx. Event.dx is the delta in the x position of where the mouse is versus where the mouse was the last time you moved it. So the only thing we're using here is these deltas, dx and dy. And then we're multiplying it by k. Now k is this panning sensitivity divided by scale. And scale comes from the current version of the state. So we could actually sort of reframe this such that it accesses state.scale. That almost seems cleaner in a way. Yeah, I feel like that kind of cleans it up. And that actually opens up the door to memoizing this call, so we wouldn't have to instantiate a new drag behavior on each render. But anyway, I'm getting a bit ahead of myself. But anyway, this computation here of scaling the delta by this constant k, this is something I had to figure out to get the panning to work at different zoom levels. So the more you zoom in, the less you want to actually move it up and down for a given delta in x and y. And panning sensitivity is just a hard-coded value here. And 58 seemed to be the sweet spot where it's relatively close to the actual movement that you get. And, you could go sort of all out here and make it so that if you grab it at the top, it moves that part of the Earth exactly. So it's not quite perfect in that sense. If you would rather make something that does that perfect calculation, you can use D3 Versor or Versor. It's pretty neat. Here's an example that demonstrates this. What I don't like about it, though, is that the North Pole is not consistent. So if you wanted to really, make it perfect, I think Versor dragging with a consistent North Pole would be the way to go. But what I've done here with the simple example that I'm walking through, I think is good enough for most cases. And also with the Versor dragging, if you try to drag outside of the globe area, it sort of has this weird, I don't know, to me it feels kind of like weird behavior where you can't just smoothly rotate it when you're outside of the globe area, which you can do here. So I don't know, this feels good enough for most cases. That's how the drag behavior is set up, which governs the panning part. Now for the zooming part. That's governed by this zoom behavior code right here. This also uses svg.call to instantiate a new instance of the D3 zoom behavior that has a zoom event listener. And that zoom event can be destructured. This is actually a two-level destructuring where you have event.transform and then transform.k, which is this scaling factor sort of a thing. And then we call setState with this immutable update pattern. And then we're updating scale to be initial scale times k. And this is actually state dot initial scale. It worked before because we're destructuring initial scale, I think, somewhere else. But again, if you wanted to memorize this, you could say state dot initial scale, and that's maybe more clear. But yeah, this is why I needed state dot initial scale. See, if you use state dot scale, this doesn't work right. You get this very extreme, almost like second derivative kind of a thing going on, and it's wrong for some reason. So that's why we have to use state.initial scale, which is always the same, times this k, which we get from the zoom event. And that seems to work pretty well. That's how you can add panning and zooming to a globe. If you have a map visualization where it's zoomed in to a particular area, the way my mind works, at least, I think it's pretty optimal to use this projection, the globe projection, but zoomed in to a particular area, because it minimizes, I think it minimizes the distortion. I mean, I'm not a cartographer. I'm sure there's people that know more about this than I do. But, this may be a good starting point even if you want to have a zoomed in, I don't know, like a county level New York map or something like that, or cities of the US. What I'm saying is you can leverage this interaction as a starting point to get your initial scale and zoom. So you can just console.log the scale and zoom and then initialize it to be that, to start with a map that's zoomed into a certain area. And anyway, if you have a map of some data, chances are, panning and zooming would add to it in some way. And you could even render things based on zoom thresholds. So when you zoom in to a certain level, certain things appear that weren't there at the zoomed out view. So yeah, I hope this is a useful starting point for your adventures in mapping.